All right, today we're going to piece together this invisible puzzle. I'm talking about the hidden rules that control the gases all around us. From the air you're breathing right now to the stuff that makes up distant stars. So let's just dive right in.
So, what do a scuba diver's bubbles in a bag of chips on an airplane have in common? I know, it sounds like a setup for a really bad joke, right? But the answer, believe it or not, is chemistry. Both of these are just perfect real world examples of gas laws doing their thing. And stick with me, because by the end of this, you're going to know exactly why those bubbles get bigger as they go up and why that chip bag puffs up like it's about to explode.
Okay, so to even start tackling this, we've got to get a handle on three basic things about any gas: pressure, volume, and temperature. Seriously, that's it. You can think of them like the three main dials you can play with. And figuring out how they relate to each other, well, that's the first huge piece of our puzzle.
All right, first up, let's talk about Boyle's Law. This one is all about the connection between pressure and volume. And honestly, it's pretty simple. If you keep the temperature the same, these two things have what's called an inverse relationship. All that means is when one goes up, the other goes down. You squeeze it harder, more pressure, it gets smaller, less volume. And the other way around too.
The best way to picture this is like a seesaw. Imagine pressure is on one end and volume is on the other. You push down hard on the pressure side and whoop, the volume side goes right up. You let up on that pressure and the volume side comes back down. It's this perfect little balancing act.
And you see this play out in the real world constantly. Remember our scuba diver? Okay, picture it. Way down at the bottom of the ocean, the water pressure is just immense, right? It's squeezing that little air bubble, keeping it tiny. But as that bubble starts to rise to the surface, there's less and less water pressing down on it. The pressure decreases, and what happens? The bubble expands, getting bigger and bigger. That is Boyle's Law, plain and simple. All right, so that's Boyle's Law. Puzzle piece number 2 is called Charles' Law. Now, this time, we're going to hold the pressure steady and instead look at the relationship between volume and temperature. And here's the key difference. Unlike Boyle's Law, these two are buddies. They have a direct relationship. They always move together in the exact same direction. So think about it like this. When you heat up a gas, what are you really doing? You're giving its little molecules a ton of energy. They start zipping around like crazy, pushing outwards, and boom, the volume increases. Now cool that gas down, and those molecules get all sluggish. They slow down, huddle together, and the volume shrinks. They literally rise and fall together. It's exactly how a hot air balloon works.
Okay, so we've got two major pieces of our puzzle on the board now: Boyle's Law and Charles's Law. That's awesome. But what happens if you want to mess with both pressure and temperature at the same time? Life's not always so simple, right? For that, we need to start snapping these pieces together to build something way more powerful.
So let's just do this step by step. We know from Boyle's Law that volume is proportional to 1 over P. And we know from Charles' Law that volume is also proportional to T. So if we just kind of mush them together logically, it makes sense that volume has to be proportional to T times divided by P. See how that works? It respects both rules at the same time. And putting that all together gives us this incredibly useful formula called the combined gas law. What it's really saying is that for a set amount of gas, if you take its pressure, multiply it by its volume, and then divide by its temperature, that number is always going to stay the same. It's a constant. And that's super powerful because it means if you know the starting conditions, let's call that state 1, you can predict exactly what the final conditions, state 2, will be, no matter what you did to it in between. Okay, so we've got pressure, volume, temperature. We're doing great, but there's a missing piece here, isn't there? We haven't talked about the actual amount of gas. I mean, how in the world do you count something you can't even see, like individual gas particles? Well, chemists, being the clever people they are, came up with a really brilliant solution. And that solution is a unit called the mole. Now, I know the official definition sounds super intimidating and complicated, but trust me, the idea itself is really, really simple. A mole is just a word for a number, a specific quantity. It's just like how a dozen always means 12 of something. A mole is just the chemist's version of a dozen, except, it's a way, way bigger number. So just how much bigger are we talking? Well, there it is. 6.022 times 10 to the 23rd. That crazy thing is called Avogadro's number. And yeah, that's a 6 with 23 zeros after it. It's just a mind-bogglingly huge number.
And that's how many tiny little particles are packed into just one single mole of a substance. And here is the absolute key thing to get about the mole. It's all about the number of things, not how heavy they are. Think about a dozen bowling balls versus a dozen feathers. They both have 12 items, but their weights are wildly different, right? It's the same here. 1 mole of ammonia weighs about 17 grams. 1 mole of carbon dioxide weighs 44 grams. Totally different masses, but guess what? They both contain the exact same number of molecules, that giant Avogadro's number. All right, this is it. We have all the pieces of the puzzle laid out in front of us. We've got pressure, we've got volume, we've got temperature, and now we have a way to count the actual amount of gas using moles. It is time for the grand finale. Let's put this all together and build the one equation to rule them all. So let's do a quick recap. We know volume goes down when pressure goes up. That's Boyle's law. We know volume goes up when temperature goes up. That's Charles's law. And now we can add the last piece, Avogadro's law, which says volume goes up if you add more gas, more moles, which we call N. See, everything points back to volume. All these relationships are pointing towards one single, beautiful, unified equation. And there it is, PV equals nRT, the ideal gas equation. This is it, folks, our completed puzzle. It's so elegant. It perfectly connects pressure, volume, the number of moles N, and temperature. And that R in there, that's just a constant, a special number called the ideal gas constant that makes all the math and all the units play nicely together. This one little equation, it's basically a cornerstone of all modern chemistry. And one of the coolest things about this equation is that it gives us an amazing shortcut. See, scientists have this baseline they call standard temperature and pressure, or STP for short. It's basically 0 degrees Celsius and regular old atmospheric pressure. And at STP, it turns out that 1 mole of any gas, doesn't matter what it is, will always take up exactly 22.4 liters of space. That is such a handy number to have in your back pocket. Okay, all this theory is fantastic, but what's the point if you can't use it, right? So let's take everything we've learned and actually solve a real chemistry problem. We've built the toolkit, now let's put it to work. All right, let's walk through this. The question is, if you have 40 grams of hydrogen, how many grams of water can you make? First things first, you look at the balanced equation. It tells us that for every 2 moles of hydrogen we use, we get 2 moles of water. Simple enough. Okay, step 2. We've got to convert those moles into grams, something we can actually weigh. Well, 2 moles of hydrogen gas weighs 4 grams, and 2 moles of water weighs 36 grams. So there's our magic ratio. For every 4 grams of H2, we get 36 grams of H2O. Now for the easy part, we just scale it up. If 4 grams gets us 36, what do you think 40 grams will get us? You got it, 360 grams of water. That's it. See? By understanding the concept of the mole and using these balanced equations, we can predict exactly how much stuff we're going to get. This isn't magic, it's not guesswork. It's the incredible predictive power of chemistry. So we started out with this invisible puzzle, the gases all around us. And piece by piece, pressure, volume, temperature, and the all-important mole, we put it all together. We built this amazing tool that lets us predict the behavior of the unseen world. And it really makes you think, doesn't it? I mean, what other invisible forces are out there shaping everything around us, just waiting for someone to come along and figure out how their puzzle pieces fit together? Thanks so much for joining me on this one.